Hey guys, one more quick video now just to tie together the bonding. So we've just talked about bonding and why it occurs, and we've sort of said that bonding occurs because elements don't have a full outer shell and they try to share electrons, which is called covalent bonds, to have a full outer shell, or they give and take, they transfer, and that's called ionic bonds. We learned very quickly just then that covalent bonds occur between the nonmetals because they're close to having full outer shells, so they're more likely to share and not give them up. And we learned that ionic compounds form between the metals, which is really, see this yellow jagged line, anything this side of metals, they're good at losing electrons, and the non-metals are good at gaining. And so we learned that that is an ionic bond, where there's a transfer of electrons. I have an electron, I give it up to Mrs. Levy, who's behind the camera, so I'm going to throw it to her. She takes it, I become a positive ion, Mrs. Levy's a negative ion, and we stick together because of electrostatic attraction. The purpose of this video is just to tidy up what that looks like in the real world. Okay, I'm going to start with this guy. All right. What I'm holding in my hands right now is really what Mrs. Levy and I had made before, which looked really weird, right? This is an ionic compound. This is a compound that is made up of ions, positive ions and negative ions, and they're all bonded together. If you can see the green, I don't know if you can see this on the video, but if you can see the green pipes, they indicate the bond that is held between the positive ion and the negative ion. Now these things are cool, these ionic compounds, they're crystals. So the simplest one that you would have experienced in the real world is table salt, right? NaCl, sodium chloride. So this crystal would be made up of sodium ions who have lost electrons, that was me, and chloride ions which have gained electrons, which was like Mrs. Levy, okay, in the video. And they stick together, and you'll notice that there's not just one sodium ion and one chloride ion, right? These crystals, these ionic compounds, can make crystals as big as they want to be, right? As long as the ions are there. So you'll notice, if you could see this more closely, that every single positive ion in this crystal is surrounded by 6 other negative ions. And the negative ions are surrounded by 6 positive, and they form this crystal lattice structure. That makes ionic compounds really strong, right? Like I could, if I'm super buff and whatever, I could stand on this. It's strong. I'm not going to do it, but these are strong lattice structures. They have high melting points and boiling points. They're really hard to turn into liquids and vapors, right? So if you want to know if it's an ionic compound, first thing, do you have a metal and a non-metal? Are they joined together? If they are, ionic compound. How will you know? Well, they'll have high boiling points, melting points. They dissolve in water, a lot of them. So, you know, if you're bored at Sizzler and you want to see how much salt you can dissolve, you can sit in there and stir it up. That's what I did as a kid. And they'll dissolve, and a lot of them will dissolve a lot, right? So they're typically good at dissolving as well. That's ionic compounds. But here's the quick thing. If I cut this ionic compound in half, I still have the same compound, okay? Sodium chloride, I can crush the crystal up. It's still sodium chloride. The formula that you will write for an ionic compound just gives us the simplest ratio of ions, right? So in this case, one sodium ion, for every one sodium ion that's in this crystal, there will be one chloride to balance it out, and we'll look at that in future videos. So just so you know, sodium chloride can have 1,000 sodiums and 1,000 chlorides, or it can have 50, but as long as the ratio is 1:1. The other type of compound we talked about was when the non-metals got together, and those were covalent compounds. That's where the electrons were shared. That's where Mrs. Levy and I formed our bonds, right? So when there's got 2 non-metals and we're sharing. That makes these guys, all right? A little bit harder to see, I know, but these guys are called discrete molecular compounds. They're called discrete molecular compounds because they are discrete, okay? Unlike the ionic compound, which is a lattice, right? We can build this as much as we want. These little guys, these molecules, are discrete. This is fluorine gas. This is 1F, the green 1F, and the other F, the grey in the middle, represents the bond where they are sharing a pair of electrons. That's what we modelled before. These guys are typically going to have very, very low melting points and boiling points, okay? So I'm not going to go into all the details there, but they're the ones that are likely to be gases and liquids at room temperature. So all of these guys typically exist in those, typically, not always. Another one that you might know about is water, right? H2O. 1 oxygen, 2 hydrogens. I should have made it. I'm not going to do it, it's going to take up too much time, right? But those are discrete molecules. Those are formed between non-metals, and they form covalent bonds. Hopefully that gives you a little bit of an indication of the difference. And yeah guys, good luck and keep doing your work. Thanks guys.